into the if you look into the publication nowadays, maybe you can find some, for example, the keyword that relate to how they conducted the experiment. The main three keywords that you probably see is in vitro, in vivo, and in silico. For the first two keywords, which is the in vivo and in vitro and in vivo, you probably familiar with that. But for the in silico, I think it's a very new keyword that some of the clinicians probably do not know yet. I put two publications, which is to state the technique of the in silico, the first one here, and also here, they also use the keyword of in silico as well. So in silico actually means the simulation in computer, which means what they do or what they did everything about the experiment in the computer, analysis, everything in computer. So why we got to have the computer simulation for the dental biomechanics application? First thing, I would like to introduce one of the very good example that I always talk or share about this when I talk about the simulations. If you look into the pictures A, B, and C, this is actually the truss structures in the civil engineering or in mechanical engineering. The first truss here, A, is quite a simple structure. You have only like 1, 2, 3, 4 members in the structure. It's very simple when you try to simulate the internal force of the structure. And now, let's move to B. B here, you have the more complex structures, and you have more force act on these structures. So probably for B, you probably can calculate using your equations and engineering techniques. But for C, on the last one here on the right-hand side, you probably see that the structure is so complex, and also you have many forces act on the structure. It cannot be calculated using your normal technique anymore. So that's why you need to have the simulation techniques to solve this problem. So the in silico techniques, which is what I talk about, will be used when we have the very, very high complexity of the problem. So if you look into your body, just like in these pictures, if I want to ask you to calculate the internal force in femur bone, you probably cannot be calculated using the normal equation. That's why we need the simulations to calculate or to find this internal force within your bodies. So every bioengineering problems, we need solutions. This is our target. So we have two main different methods to find the solutions. The first one, we call it direct method, which is you do everything experimentally and physically. And sometimes you also can apply some equations to solve this problem. But this one, even is very straight away and give you 100% correct solution. However, sometimes or some application, you cannot set up the experiment just simple like this. It's probably a little difficult. Or you cannot use the equation like this to solve your problem. Sometimes it's not possible as well. So alternatively, we develop something called numerical method, which is to do everything in computer, simulation everything in computer, and also give you the solution. Although the right-hand side one give advantage to you, to do everything or postulate everything in computer. However, it gives the approximation solution, which means when you have the solution is not always 100% accurate. It contains error, which is what you need to understand, that every time you do the simulation, it will not be 100% correct. You need to verify or validate that your numerical simulation is reliable enough to use in the clinical application. So we have two techniques to validate your numerical solutions. The first technique is mechanical validation, which is you compare one case of the numerical method to experimental method. This is one way. And the second way, we can conduct what we call the convergent testing, which is you develop many different numerical model, and then you can see that the model, if you change the input of the simulation, the result is still the same or not. So the most numerical method that we use in dental application is finite element method, because it's related to solid mechanics, it's related to bone of your body, it's related to teeth, which is the solid objects. It's not the fluid objects. So finite element method is the main tools that we use for the simulations. For the finite element method, it composed of 3 steps. The first one is pre-processing, analysis, and post-processing. For the pre-processing, what you need to prepare is you need to prepare the geometries, you need to prepare the material behavior model, you have to prepare the contact conditions. And last one, you got to prepare the boundary condition applied to the numerical model. And after you prepare all these input, you just put it in the computer to analyze. Normally, it's the computer and cluster tasks to analyze and give the solution for you. In order to see the solution of the numerical analysis, we call this stage as the post-processing. So you can see that how the structures deform, how the stress level rise in the structure after you act the load on your objects. So how to model the geometry to be input in your finite element analysis? You can apply the computed tomography or CT images and develop these CT images into the 3D model. The key point is that when you develop the digital model to be used for the analysis, you need to think about the thresholding, because even you have the same images from CT scan, but if you apply incorrectly the thresholding of your house field unit, you will get the inaccurate geometry as well. So normally you need to calibrate your CT scan and to see which is the proper range of the house field unit that gives you the best accurate model, particularly for the dental application, because the object is much smaller than orthopedics. So you need to think about also the accuracy of your model also. So to get the 3D model, this is actually the summary of how we can transform the objects into the CAD model, which is composed of the object, image sectional area, data, or DICOM data. It's actually the same. And we have the thresholding and transform this thresholding into the 3D polygons and convert into nerves, and then we can get the final CAD model to be used for the finite element analysis. And for the material properties, we can either search on the literature review, or you can test using the machine directly. So it really depends. For example, if you have the literature reviews that talk about the material behavior of bone or your implant object, you probably search over that. However, the pitfall of the finite element analysis is that normally we do not consider about how the material going to be behave in your simulation. Actually, there are 3 models for the material properties. The first one is isotropic, which is you assume every direction of your material to behave the same. The second one is transverse isotropic, which is you assume that 2 directions of your material behave the same, whereas another direction behave differently. And the last one is isotropic, which is all directions behave differently. So in the publication, sometimes they assume everything to be isotropic because it's simple and it's easy to be used. However, if you assume everything to be isotropic, sometimes the behavior or the result that you get probably not reflect the real life or the real biomechanical behavior. So the best one that you can input into finite element analysis is an isotropic, which is the last one here. And you can even assign the single point on the CT image to have the different mechanical property based on the equations here. You can transform the house field unit here into the density, and then density into the elastic modulus, which is the one that you need to be input into a finite element model. So just a little more. Sometimes if you do not know the material behaviors or material properties that you need to be input in the finite element analysis, you need to conduct the testing. For example, this is the test or the sample that we use to mechanical testing like this. And then we need to put into the machine called UTM, which is Universal Testing Machine. It applies the tension force step by step until your sample break apart. So the information that we get or we obtain from UTM will be also input into the finite element analysis as well, in case you don't have the data like this in the literatures. So how you do the validations? So as I mentioned before, the finite element analysis or the numerical method, it will not give you 100% accurate. So you need to verify using the mechanical experiment. Here are some how I conducted the mechanical validation. I model the structure using the 3D printing techniques, and then I place the device called strain gauge, which is something like this and like this on the model surface. And after that, I put the load to my model, and then the deformed surface of the structure will give you what we call the strain over the structure. And I need to compare these strain values with the finite element analysis. The best case is that the value that different from the mechanical testing and finite element analysis, it should not be over than 20%. So the model that you develop is reliable enough to be implemented. Okay, and once after you get the result file which is in the post-processing step of the finite element analysis, you need to think about the parameter that you use to analyze. So the main two parameters that we use to analyze are the equivalent one-mid stress and also Tresca or principal stress and also the elastic strain. So of course the one-mid stress and Tresca principal stress focus on the risks of the structure failure, of course. And for the elastic strain on the right-hand side, we can use to assess how the bone mass add or bone mass loss over the structure. So in case you have the ductile material, for example, your titanium or stainless steel implant, you may use the one-mid stress to see how the structures are at risk of failure. But if you have the brittle material, for example, like your bone, you can use Tresca or principal stress to see how the bone going to be at risk. So this is some of the case studies. So for the first case study is I apply the finite element analysis to study the monocortical and bicortical minuscule placements in the bone rapid palatal expander. So in this study, I model two finite element model. The first one was to place the monocortical screw. And second one, I placed the bicortical screw. And what I wanted to see, I wanted to see the effectiveness of the expander. So I compare how the superior and inferior mid-palatal suture expand. So if you see carefully here on this slide, the bicortical is more effective doing the expansions. Besides the expansion, I also focus on the mini screw and apply and stress, which is I need to look at the risk of the appliance breakage or the meniscal breakage also. And also I look on the elastic strain on your right hand side to see the possibility of bone resorptions. The second case that I would like to share with you is the effect of the meniscrew locations on the performance of the bone ball rapid palatal expander to the mid-palatal suture. So in this research, what I did, I also prepare 3 cases of the finite element model, and I placed the screw differently in the different locations. And what I did, I developed the finite element model over there and gradually let them expand step by step according to the screw pitch turn. So I also analyzed exactly the same thing that I talked before, the performance of the expander for expanding the mid-palatal suture, and I also look into the stress of the appliance as well. So this is another application, but it's not related directly to the orthodontics, but more for the surgery. So in this case, I apply the finite element analysis to see if I have 2 different fixation for the mandibular symphysial fractures. The first one was the reconstruction plate, which is here, and the second one was the reconstruction, the 2 mini plates placed here. So over there, the mesh model here is the model that I developed and apply the constraint and force on the model. The P1 to P12 is the place that muscle force and occlusal force apply on my finite element model. And what I wanted to see the stress level exhibited on the implant here, and also how the fracture gap deform after I apply two different fracture fixations. For the fourth case, this is about the implant application. So what I did, I also designed three different cases of the finite element model. And also I have the splint and non-splint model here, and apply the force. In this research, I also validate the model here using the mechanical testing to see how accurate of the finite element model were. So I also model the different implant diameter and also the cortical bone thickness to see how these two demonstrate the effect to the overall suprastructures. And for the case study 5, this is to compare the conventional implant, which is the screw-like one, and also the porous structure one. So what I did, I also created 5 different porous models, ranging from porosity of 58% to 79%. And then I put the occlusal load, like the oblique load, on the implant, and also the lateral load on the implant as well. And what I wanted to see the risk of the implant failure, which is here, the axial loading, and this is here the lateral loading, and also how the different porosity of implant act differently to when we have the axial and lateral loading conditions. And here it is the marginal bone stress, which is you can see that if you put the solid structures, for example, like the screw-like implant, there was the very high stress around the marginal bone. But for the porous structure here, it can reduce the marginal stress around the bone. So it helps you to prevent the marginal bone loss over the time. And the case study 6, it is about to develop the new type of the clamp. So the difficulty is that no one knows how to expand the clamp in the simulation. So what I model the cone here to help the clamp expand step by step, and then clamp at the tooth around here. So what I did, I also focus on the stress on the enamel and also dentin layer for the different type of the clamp, which made of metal, PEEK, and mix between PP and NR. For the case study 7, it's not related to the finite element model, but it's more about the artificial intelligence. So for this research, the objective was to predict the skeleton class based on the 9 parameters here. You can see here. And then the first step, we measure the data step by step all over 9 parameters. And after that, we develop the AI model to help classify the skeleton class. So we have tried 7 AI models, which are random forest, gradient boosting, logistic regression, ANN, decision tree, SVM, and KNN. And we only selected the best accuracy to predict the skeleton class after that. However, for this research, the most time-consuming part is the data collection, because we needed to make sure that all data that input into the AI model is fully accurate. Otherwise, it will give you the bad AI model as an output. So the pitfall in finite element analysis is that sometimes, let's say that the software is probably easy to use. However, if you input the incorrect data or incorrect information into analysis, it will give you the incorrect result as well. So according to my experience, some of the researchers got the wrong input unit. For example, if you try to model in millimeters, sometimes when you input the material property is in different unit. So you got to be aware about that. And also you need to check that the model that you use for the analysis is completed. Sometimes it's not so complete, and then we try to put into the analysis. Even it gives you the solution, however, that solution is wrong. So the last one is about vectors. Because when you search over the publication, you see the vector force act on the structure. However, the X, Y, and Z is probably different from what you set up in your actual setting. So you need to check also the force vector that you apply to your model to make sure that it will be correct. So thank you, and this is my contact information. You can contact me at my email here and telephone number over there. And I have the official organization Facebook and LinkedIn and also website over there. Thank you very much for your attention. Maybe we have 5 minutes for the questions that probably from the floor, if you have many questions.
Các quý bác sĩ có những câu hỏi hoặc thắc mắc nào có thể giơ tay hoặc đặt câu hỏi, quét mã QR phía cánh trái màn hình để gửi câu hỏi tới báo cáo viên. Mọi câu hỏi của bác sĩ sẽ được giải đáp. Trân trọng cảm ơn.
Dạ, quý bác sĩ, chúng ta có câu hỏi nào đặt cho báo cáo viên à? Báo cáo viên là một trong những lĩnh vực liên đới của chúng ta. Ảnh không phải là bác sĩ nha khoa, không phải là nhà lâm sàng như chúng ta, nhưng những lĩnh vực nghiên cứu của ảnh sẽ mang lại những ứng dụng cho chúng ta. Đó, cho nên cái này nó cũng mới mẻ là lạ. Và mời anh Tân, trong đây có Tân đây.
In the manufacturing side, we always think about that one. So thanks for your presentation. In Thailand, you have like experience connect to the factory and manufacturing something like that from your, let's say, like your research about simulation in silico and transfer to manufacturing something like that?
Yes. Actually, when
you have one example of that.
Okay. For example, when I will give like 2 examples. So the first one, the fracture fixations. So in some case of the trauma case in your mandible or maxilla, sometimes we cannot use the standard implant to fix the fractures. So what we need to do is that we need to design the customized implant to fix your fracture. So we need to simulate the conditions that we need to fix first, and then we try maybe over 4 or 5 different situations, and then we translate the one which is the best design into the manufacturing. This is what we did for the customized implant. And also for the dental implant here, we also design using the finite element analysis first, and we simulate the different scenario to make sure that it will withstand the occlusal force. After that, we also translate that design into the manufacturing as well.
Thank you.
Thank you.
Okay, can you see it? Can you see my screen? Can I? Okay, so I think this is a yes, I will begin. So, yeah, Viet, thank you very much for your kind invitation. I am very glad that I can speak at least online about my topic. And my topic is about the CAD/CAM workflow in orthodontics, what digital orthodontic is now, and what possibilities we can do in the future, or right now, or even in the future. So, short introduction about me. I am born in Korea, but I did all my academic career in Germany. And in 2019, I opened my own orthodontic practice here nearby Frankfurt. And since then, I'm speaking about digital orthodontics. And as my name is a little bit complicated, you can just call me Paul if you see me wherever in the future, and I'm very fine with that. So this is where my practice is located. You see, this is the Frankfurt airport, and just nearby is the city Neu-Isenburg, and I'm very close to the Frankfurt airport. So if you ever have the chance to visit Germany, you are warmly welcomed to visit me in my office. So I also had the very big chance that Professor Nanda visited me in my office. It was a very, very big honor. So it's very close. It's nearby Frankfurt. So you can visit me anytime if you're in Germany. Okay, just a minute. Okay, good. So let's begin with CAD/CAM. What does CAD/CAM mean? You know, CAD/CAM means computer-aided design and computer-aided manufacturing. And why is it quite interesting in orthodontic? For me, the most important point is that we have the possibility of maximum customization. We are not restricted by any manufacturers, but we can do just as we planned, and also as the patient needs. And this is a quite nice paper from the Children's Journal, and it is written, as you can see, designed and printed in tailor-made fashion and according to the patient's needs. I think this is a very big advantage. So we are not restricted about the appliances, and we can just design and plan them just to meet the needs of the patient. I think this is everywhere almost the same in the world, that we are lacking of employees, especially dental technicians who can do for us the work. So I don't think that we can replace them at all, because we will need dental technicians, but maybe in another way. And the digital technology helps us to support them and to overcome a little bit of the lack of employees, because they can not substitute, but also just support our dental technicians. So maybe we need only 2 instead of 3. The workflow is simplified because we have all in our hand, from designing to manufacturing, and that makes us, of course, a little bit more flexible. And in some cases, we can also optimize the biomechanical properties, and I will just talk a little bit about it, because I have about biomechanics to be honest, but I will just tell a little bit how we can optimize in some specific cases. If we talk about manufacturing the whole CAD/CAM process, then in the past it was like, if we have an idea, we needed an external company to make it reality, right? The company has to design, make prototypes, produce, manufacturing, and so on. So in the last, the customer is again our part. But with the development of the digital technology, we are now able to make all the process in our own office, like designing, prototype, also producing, and then delivering by customer. So for sure, we can't do everything in-house, but I think a few steps we are now able to get a few parts in our own office, so we can also make our our workflow better. The advantages are we are more independent because everything lies in our hand. The workflow gets simple and faster, and we can reduce the cost because we don't have to pay to external companies. The whole budget is in our office, and of course, it is fully customizable. On the other side, there are also disadvantages because the learning curve is very flat. We will need time, and to get further knowledge of CAD, we will have to learn new stuff because we are orthodontists. We never learned about computer design or something like that. And in the beginning, the investment costs are very high because we have to buy some software, we have to buy 3D printers and so on. And this is very time consuming and also cost intensive. But I would say this is affordable, and this is a very good investment to invest in the future and to overcome some limits in orthodontic treatment. So let's begin with designing. There are several orthodontic softwares, and I tried a few of them, but from the German side, we are stick to OnyxF because OnyxF is a German software, and OnyxF is some kind of like the Switzer knife. You can do everything, almost everything you can do with OnyxF. It is not easy to get into it, but if you know how to manage the software, then you can do almost everything from splint, to surgical plannings, or also appliance design. Almost everything is possible with that. And I mostly recommend also to get a little bit knowledge about other CAD software like Fusion, Blender, or Meshmix or whatever. And for me, the Fusion 360 was the most simplest software to learn. So I stick with that because OnyxF has a little bit kind of limitation, and to overcome this limitation, it is very helpful if you can deal with the extended software. Let's go to the part of manufacturing. Because this is the very interesting part. And in 2013, Obama already said 3D printing has the potential to revolutionize the way we make almost everything. And I think he was definitely right, because if you think that the first 3D printer which has been officially announced was 1983, then about 42 years ago. Now we have so many 3D printers, we have so many different kind of 3D printers, and now we are able to do it in our office or even at home. And these are my good friends, and I think we had the one sentence, what can be printed has to be printed. And I try to print almost everything, and I will show you what can be printed or what you should not print, what's better. There are a lot of 3D printing technologies, and actually we don't need to know everything, because for our orthodontic purposes, I think these three are the most important: SLA, FDM, or DLP, and also some kind of metal printing technologies. But these are the most common technologies regarding 3D printers, and I will dive a little bit deeper into regarding 3D printers. There are a lot of questions regarding 3D printers actually online, and everyone is asking what's the best 3D printer for this purpose, what's the low-cost 3D printers, and actually there is no answer. For me, I have a little bit experience in 3D printing right now, and I can say they are only good printers and also better printers. But the best printer in the end is the printer which you have in your office, in your hand, because you know how to handle it, you know how to deal with it if you encounter any problems. So I think it is important to know how to deal with your 3D printer. In my very humble office, I have a few 3D printers, and if you ask why I need so much, maybe Viet has more than me, but I also have a few, and there's a very nice song text, and it says too much is never enough, because we are addicted to toys, and it is some kind like when women have a lot of shoes, so we like 3D printers instead of shoes or bags. But to be serious, every printer has its own purpose. Like LCD printer with large build plates, these are this one and this one. I use them for aligner models, laboratory models, or graphy aligners. And these two guys are the small ones for small parts like surgical guide, IBT trays, and so on. And I got also 2 filament printers, and with the filament printers, I do some study models or laboratory models. So actually, there is no all-for-one printer. Every printer has its own purpose, and I usually recommend to begin with 2 printers, because small and bigger one, because you should not also mix some biocompatible resin with non-compatible resin, because a non-compatible resin should not used in the mouth of the patient. So you won't have that one printer to print everything. And if you compare SLA to or LCD to FDM, then this is some kind of resin printer. You have resin. Every layer is being cured by UV light, and then it is done. On the other side, the filament printer, the filament got melted, and then it is accumulated layer by layer. So it is some kind of different technology. And to compare both, I can say I will start with the LCD printers. The structure is very accurate. We have a very high precision of the objects, and this is not comparable with filament, because as LCD resin printer are much more advanced. It is also faster as a filament printer, so because you are making layer by layer, and a filament printer has to draw the lines line by line, so a filament printer takes longer. And what's very interesting is resin is some kind of liquid, so you can mix it like a good cocktail. You are mixing cocktail to get a better taste, and you can also mix resin to get a better mechanical property. So in my case, for example, I used the Key Ortho IBT and the Key Splint Soft. The IBT resin from Keyprint is a nice resin, but for me it was very soft. So as I know, we can mix it, and as I know that both resins have the same printing settings, I just mix it 9:1, and it got a little bit harder, and for me it has a very good feeling. So these are some kind of, if you have interest and if you want to play a little bit about resin like me, then you can mix some resins if you know what you're doing to get a better mechanical properties you're aiming for. And in resin, there are more medical certified resins like surgical guide or crown resin or so on, and there are not so much in the filament part. On the other side, it is of course more work because of the post-processing. You have to wash it, you have to cure it, and you have to be very careful because the resin is very toxic and it has some kind of uncomfortable odor. The cost is a little bit higher than filament, and in general, you got small build plates. So if you want to print a bigger part, then a resin printer might not be suitable. I'm printing with the resin printer like IBT trays or surgical guide and aligner model with attachments. Actually, I print every aligner model to thermoform with a resin printer. But if you are thinking about printing it with filament printer, it is possible. But the filament printer, as you can see, the attachment expression are not so good as the resin printers, right? The resin printer, the attachments look very nice, but in filament printers, you can have some problems, like in this case, because the filament got melted, it has to drive the attachments, and the expression might not be so accurate as the resin printer. And if you print also crown denture base or something like that, or direct printed aligner, of course, then the resin printer is the way to go. But I also love my filament printers because you don't need any post-processing, right? If it's printed, then you can just use it. There is almost non-toxic and no odor. And important to know is almost, because you are melting plastic. That means there will be some kind of particles, which is not so healthy for our body. So it is recommended to have a closed chamber with some kind of cold filter, so that the particles are being filtered. The filaments are usually a little bit lower in cost. And what's very interesting is the multicolor printing. As you saw it in the time lapse, you can print parts in many colors. And usually you have a larger build plate. That means if you want to print some bigger parts like functional parts or whatsoever, then a filament printer is much more easier, because you can print a bigger part easier than in a resin printer. On the other hand, fine details you won't be able yet you won't be able to print, like an IBT tray, an indirect bonding tray. You won't be able to print with a filament because the details are not so good printed. It takes more time, as I told you, because if you want to print, let's say 8 aligner models, then in a filament printer it might take about 3 to 4 hours, and in a resin printer you can print them in once, and then it takes only 20 minutes. The material, especially for the medical products, are not so much, because there are some filaments like for denture or for impression trays, but it is compared to the resin not so much. And a filament printer is good for laboratory models, study models, a prototype, or large volume objects. And if you decided if LCD or filament printer, we have to consider why are there cheaper printers and why are there expensive printers. And regarding the result, I can say every printer is doing its job great, and the 3D printers got so much better in the last years. So in accuracy, I don't think there's any clinical significant difference, and you can actually use any printer. But if you get a closer look on that, a low budget printer has a very good quality for a low price. It is usually smaller in size, so you can get maybe more in your office if you lack of space. It is easier to repair because the cheaper printers, they are built up very easy, so you can also repair it if possible, if needed. And most of them are open system. That means you can use every resin which you can buy, and this is also a very good advantage because you are not restricted on any specific resin. The user community is very wide, so if you encounter any problem, then it is much easier to get an answer quite quickly, because you can just ask in the forum or in the internet, and you will get an answer quite in a few hours. On the other side, there is no support, and if you don't know how to deal with the 3D printer and you encounter a problem, then you will need help from the outside, and you won't get them. And therefore, it is some kind of time consuming, because you have to learn this, you have to get know with the 3D printing techniques, and this might be time consuming. This is something, a very important part, because I think it's the same for you, orthodontists. We don't have so much time to deal with things other than orthodontics. And it is not so easy to dial in the setting. That means if we use various resin, like we are using model resin, we are using crown resin or whatsoever, then for every setting, for every resin, the settings are different, and we have to find out if it's not saved. So this might be also time consuming. That means it is less plug and play. But the modern 3D printers, they are getting better and better, and they are coming close to almost plug and play, which makes for the normal user very easy to use them. Well-known companies are Lego, Creality, Frozen, and so on. And I can say the printers, they are very good. They are working very nice. I also have some of them, but actually you should know how to deal with them and how to set them up. On the other side, the high budget printer, that's actually the reason why why, for example, in the German orthodontists are aiming for high budget, because it is almost plug and play. The German orthodontists, they like to buy something, push on the button, and it's work. But even the high budget printer, they are actually not perfect plug and play. You still have to know how to deal with them. But you got also local support, because they are expensive. They are sold by dealers, and the dealers, they also provide some support. That means it saves a lot of time. You don't have to deal it by your own, but you have your support, and you got plane. So you are saving a lot of time. And especially the high budget printers, they have their own slicers, and in the slicers there are all the settings from the resins which can be printed with the printer. So you don't need to handle the adjustments with the settings. But usually the printers are very big, so you need a little bit more space. And if there's a problem, then it is not so easy to repair, because it is a very complex device. And the user community is very small, because they're expensive printers. So if you have a problem, then you are very dependent on your local support. Closed environment is changing in my eyes, because the well-known closed environment printer was the Formlabs, and Formlabs has shown with this new Formlabs 4B that they also get open. You can now use third-party resins also in Formlabs. They switch from SLA to LCD, because they see, okay, SLA takes a lot of time, and the new Formlabs 4B is a very great printer, and Graphy is also using now the Formlabs more than the Unis NB. So well-known companies are Formlabs, SprintRay, Race3D, Aziga, and so on. They are very reliable printers, but also a little bit more high cost. So now we talked about CAD and CAM, the workflow. Now let's take a look what we can do with CAD-CAM workflow in our office. The first one is some kind of articulator. I was looking for some virtual articulator which can be printed, and just to articulate a model. It doesn't need to be very precise, but I just wanted some model which can be articulated. And the digital part I didn't like so much, so I designed my own one. And I designed it with Fusion. For me, it was important to make it in 45 degrees, because the 45 degrees makes it possible to print them without supports, because I hate them. I hate supports, and I want to avoid it if possible. And I can import it in OnyxF as an STL file, and then it can be exported together with the model, and it can be printed either with the filament or resin printer, and then it can be stacked together. And as you see, the printing goes quite easy. And this is when it's ready. Then you just stick them together. It's quite an easy process. And then you got some articulating model, right? And I use them mostly for some kind of herbs appliance or Mara appliance to check their functionality, if it's working or not. And for this purpose, articulating model is quite nice. The next thing is so-called bite bumper, and you know them. It's called bite bumper, bite rams, bite turbos, whatsoever. And I'm a big fan of the prefabricated ones. But the problem is, in this distance, this place is very, very small. It's about 5 millimeters. And I think you all know the problem. The patient, they are biting behind it, right? They are biting on this side, and then they are falling more back in class 2. So I was looking for some bigger one, and as I couldn't find something, and maybe you know that we as Korean nature, we are very good in copying things, and I just copied them. I copied them in Fusion 360. Again, I make it a little bit longer for 8 millimeters, and this was exported as an SAL file again, and I can print it out with some crown resin. The crown resin has a very good stable mechanical properties, so it is very suitable for such things. And then you can print it out and post-processing according to the manufacturer guidance. And if you take a look, this is the original, this is printed. I think my copy is not bad. So I always have them in place, and the adaptation worked quite fine. The next thing is some kind of insertion guide, and insertion guide I use very often when I do some relative mini screws. And with the insertion guide, to design and to print in Office is not so complicated, but we have to know when do we use insertion guide or not. And there are the one visit and two visit protocol. And the one visit protocol means that we are putting all in at once. Like we are inserting the mini screws, we are adapting the appliances, and this is done in one visit. Two visit means we are first inserting the screws, then we take an impression or scan with scan bodies, and then we are putting the appliances. So for me, as a quite lazy orthodontist, I aim for the one visit protocol. I like to do it at once. The advantage is it is time saving for sure, because we only need one visit, and it is less effort because we can do it at once. On the other side, it is not so precise. And if you're inserting the screws not so precisely as you planned, the appliance won't fit. Then you have to do two visit either. So this might be more time and cost consuming, especially in the beginning. When you begin with some from one visit protocol, you might be a little bit frustrated in some cases, and then you need to scan again. But for some kind of distal or major slider, it is quite suitable because these are appliances which doesn't require so high precision. On the other hand, the two visit is very precise. I never had problems with two visit protocol. The appliance fit on every time. So almost no correction is needed, but of course, you need at least two visits. You have to insert the screws, either if it's freehand or with the insertion guide, and then take a scan or impression again. And on the next visit, you can apply the appliances. And some kind of like MARPI or TED anchored appliances is quite recommended to do it in two visits, especially when you do it for the first time. It is better to get a little bit used to two visit protocol, and then you can switch to one visit when you feel better. So if you do some insertion guide, it is important that you design the arms as thick as possible, because during the insertion, you got some kind of insertion torque. And if you don't stop in the right time, then this might be break because the force is very hard. The occlusal rest, they have to be very stable. Otherwise, you got not accurate position of the screws, and the appliance won't fit. The guiding tube should be scaled a little bit bigger than the screw holder, and I would recommend to do it about 0.1 millimeter larger. That means my screw holder from PSM, it is called, has a diameter of 5 millimeters, and I scale them to 5.1 millimeters. Otherwise, you got too high friction, and the screwdriver won't won't slide in. And for such kind of work, I learned it from Björn Ludwig. You can use some kind of calibration tool. This is a ball, it is called, and this is calibrated to 5.1 millimeters. So after I printed the surgical guide, I can go through with it, and then I have exactly 5.1 millimeters. Why is it important? Because if you do some kind of one visit protocol, as I told you, the screw has to be very precise with the insertion guide. And there are some papers, like they say CAD/CAM based surgical guides have sufficient accuracy, and also the sterile mini implant insertion guide is reproducible and clinically acceptable. This is a very nice paper from Italy, and what's very important is the clinical steps. The clinical steps have a bigger influence and need to be carefully evaluated. That means, in the end, we as orthodontists, we are the one who are inserting the screws. So it is very important that our experience is good enough. Otherwise, you will undergo some trial and error till you have a good feeling. What's very interesting is this paper from Germany, and they make some cadaveric study, and they say vertical deviation of more than 2 millimeters. More than 2 millimeters, extremely high. In general, I got, when it's high, it's about half millimeters, like 0.5 millimeters. But what is interesting about this paper is that in the reality, the vertical dimension is the most difficult part to get accurate. The horizontal dimension is quite precise, but the vertical dimension is difficult because if you stop too early, then it is higher, and if you insert too much, then it is lower. So it is very important to get the right timing. And for this purpose, I made some modifications for me. This is my screw holder from PSM. And as you see, I try to copy it again in Fusion. I make it as precise as possible. And then I import it in OnyxSafe to use it as a subtracting part, as a negative part. That means these part, the yellow parts, are being subtracted in this case, and you see this engravings. For me, this is a very important part because with this, this is some kind of tactile and also visual feedback. So I know when to stop with inserting. And I tested on some dummies, also advantage of 3D printing. I printed out some models and worked on that and practices and see, okay, this is the timing when I have to stop insertion, so I have a very precise vertical control. And we are going to some kind of SLM printed appliances, and metal printing is very interesting. This is the only thing we can't do now. For now in our office, we have to outsource them to laboratory because a metal printer is very expensive yet and very big. So it doesn't make so many sense to have a metal printer. So these kind of appliances are outsourced. And in metal printing, these are very standard appliances like a MARP or RME, a TED-based TPA, lingual bar or Mara, and space holder, and also Herbst appliances. So these are standard appliances which I do on regular basis in my office. But I want to go through with some very special appliances, some customized appliances, because then I can show you how to meet the needs of the patient. This is a tongue grip. I learned it from the great Simon Graf, and he showed this once in a congress, and I asked him, how do you design them? What's the secret behind them that you can print them at once? And he told me that this ring, you have to make a very small bar in it, and then you can print this appliance at once. And the ring got loosened and it is movable. So for patient who has a tongue problem, it is very interesting because they can play with the tongue on the ring, like Castillo Morales once explained, and then it is quite effective. And the very nice thing is you can print the whole appliance at once. And on this patient, it worked quite fine. Of course, I think the natural eruption also helped, but I think the tongue grip also hold back the tongue, so the eruption could go very nicely. This case, as you can see, the severe problem is the mesial rotation and the mesial movement of the 2-6, and the lower jaw was looking just quite fine. So I was thinking of, okay, where do I have to move the 2-6? And I make some simulation on OnyxSafe, and as you can see, it is more derotation than distalization. So actually, I have to make a derotation movement. And for this case, biomechanically, it is better to have a pushing force on the buccal side. For distalization, what I know is some kind of pendulum appliance or Bennett slider, but they all have force applied in the palatal side, which can cause more derotation. So in this case, I was thinking of making a device with the push mechanic on the buccal side. And this is the design what I have done in OnyxSafe. It is a dental anchored metal printed device, and I make a guided tube, so the derotation might get we can control the derotation, and in case that we need a little bit more distalization, I also made some tube and a sliding arm, so we can distalize in the end a little bit more. And as you can see, the red one is the current position. This is the aim position. And if you make a good derotation, then you see there's almost no distalization. It's just some kind of derotation. And I bended a 1.1 stainless steel wire like this. And it was adapted together with the frame, which was metal printed. And I put also 240 gram 90 coil on the buckle side. And we started with derotating. And what's very grateful to the young patient is they are reacting very nice. As in this case, after 1 month, we see a little bit more derotation. The space got bigger. And after 4 months, we got a total derotation of the 2/6. And if you make a superimposition, you can see we still need a little bit more distalization, but the derotation went good. On the other side, what's very interesting is also the anchorage loss of the whole other part. And I was grateful that we didn't lose the midline. So anchorage loss is something which I expected because of the biology, but the derotation went well. And then here we see the white one is the current position, the blue one is what we have achieved, and the pink one is where it has to go. So we need a little bit more distalization. And for this purpose, I told you I designed the tube and the sliding arm. And this can be easily done chair side. Like this is a mobilizator, also a 240 gram 90 coil, and this is a self-bendable sliding hook from Björn and Atizi, and then I put it in chair side, and then we got a little bit more distillation, but also a little bit more anchorage loss. But I think now we have place enough to get the premolars erupted. And I could publish it as a small pearl with my good friend Till in the JCO last year. Next case, very similar case, but a little bit severe because we have also transverse discrepance, and we need to expand it and also derotate it. And I made special RME, a standard RME, but I made some slots on the buckle side to put in later a spring coil and to get rid of the arm so I can derotate the 2/6 again. But then I got a little bit frustrated because when we fit it in, it didn't fit. And the reason is we scanned in November and we had to wait 2 months because the patient didn't appear. And then meanwhile, the 2/6 got rotated more. And this is what you have to take into account when you deal with metal printed parts. Don't wait too long, especially in such cases, because if if the blinds don't fit, then you can't change it because SLM printed part is very rigid. And so I had to cut it here and cut it here and weld them together so it fits again. And then we could start first with the transversal expansion. And then after that, I put 0.01290 wire and spring coil, and then cut out the arms. And then it was derotating, and the derotation went quite well. It got a little bit more distalized, but then the 6/4 got loose. We have to remove the appliances, and now we are looking. We just stabilize this for retentional use and then waiting for the premolars to erupt. Next case, also very similar case. Maybe they are everyone is coming with the same problem to me. This was a young girl, 9-year-old, and this time it was a 1/6, and the panoramic looked a little bit strange. So I was I was thinking of maybe it's a potential PFE, primary failure of eruption. And as you know, in this case, you are not allowed to move anything because then it got ankylosed. We don't know why still now, but if it's a PFE, you are not allowed to do any orthodontic forces. So we were waiting, and about 8 months later, we see, okay, something is moving, something is changing, and then we got convinced that it is not a PFE, so we could go on with the orthodontic treatment. And sometimes it doesn't need to be very complicated. You can do, in this case, I put some screws on the pivotal side, designed the one arm lever here. And my aim was to make some power chain in this direction to upright, distalize, and also derotate at once. And this is how we started with the power chain. Very simple mechanic, but the derotation and the uprighting went well. And about a few months later, the uprighting was nice. We have a nice class 1 occlusion there. And thanks to the uprighting, we also got a little bit more correction in the vertical dimension. So sometimes it doesn't need has to be very complicated. And my very good friend Oliver Liebe has planned this one for his patient. You can also do it on CBCT base. And as I just wanted to show, there are no limits. You can do just as you want and just as the patient needs it. And when we talk about CAD/CAM, I think direct printed aligner is a very hot topic now. And I know Viet is a very special expert in this. I do also some direct printed aligners because the workflow is very simple. We got better biomechanical properties. And we have a lot of treatment options by utilizing auxiliaries. On the other side, we have also to be very careful what we are doing, especially the post-processing workflow, because the resin is very toxic. And a lot of cases are reported regarding allergic reactions and other tissue reactions, so on. So the post-processing part has to be very strict. And maybe the staging strategy has to be adapted a little bit because the force is different than a thermoform aligner. And becoming a manufacturer means also higher responsibility, especially what the post-processing regards. And if we make a direct comparison, then it is some kind of compared between stainless steel wire and night-tie wire, because a thermoform aligners is applying force on the first moment. But the printed aligner has some kind of shape memory effect. That means on a specific temperature, it is getting back in form, and then the force application begins. So it is some kind of night tower. It is reactivated every time when the aligners get in the mouse. And what the biggest advantage is there's a constant apply of light forces. This adapt more to the nature of the tooth movement, and it is a constant orthodontic force, and we got some geometric stability. And this is a very nice paper from St. Louis from Professor Kim, and they make an in vitro study about what kind of thickness difference can adjust the tooth movement. And they found out that in this case, when you want to move this one, the 2-1, and make the buccal side thicker and the palatal side of the neighbor teeth thicker, then you got better anchorage and better force, so you can control the tooth movement better. That means we can change the magnitude of forces and moments, which means that we can increase the predictability of the tooth movement. Sure, the studies are coming right now every year a lot, which is very nice, but we are still in the development phase, so we have to wait. I think we still have to wait to see what the printed aligner will be. I have a very simple case. I do actually very simple cases with that because I still don't feel very safe with it. And I do very simple cases like this lady. She just wanted to get this one back and this one on position and this one a little bit intruded. So I made a very simple setup. With this pressure point, I tried to derotate it a little bit. I made an attachment to extrude it a bit, and also pressure points on the laterals to push them in the arch. And as you can see on the 2-2, I made some intrusions, and this was very interesting. I also made some biturbos, so we got additional anchorage for the intrusion. And this is how we started. I planned 8 steps, and luckily, after 8 steps, it looks quite nice. And very interesting is the intrusion of the lateral. It works quite nice thanks to the biturbos. And if you take a look on the superimposition, you see we really got some intrusion. It was about 0.7 millimeters, and the teeth are standing just as we planned. And with direct printed aligners, I think we are going forward. It will be the future, but I think it will take a bit time, like the mini implants. For instance, in Germany, the mini screws begin in the beginning of 2000, and we are now 25 years in it, and not even half of every German orthodontics are using mini screws. So I think it's the development of the graphene aligners or printed aligners will be a little bit the same, and the competitors will come. Lux Creo is a very interesting alternative. ODS and other, they will come in the next years. For now, Graphie is the world best. Lux Creo is a very serious competitor, and I'm very looking forward to how the development will go. What else can we do? I'm not sure how familiar the Bennett slider is in your country, but in Germany, because it's the inventor is a German professor, it is a very well-known appliance to distalize the first molars. And this one is the very classic parts. Everything you can buy. You only need the bands. And I made in the last times a lot of modifications. I made them 3D printed. I changed the bands, and I made it self-designed, and also I made it 3D printed. I got the idea from Ujima. He showed in one of his presentations a few years ago that he's also testing the crown resin from Graphie and printed out the Bennett slider. And I think, wow, this is very nice. So I have to copy it. And this is the design in Onyx F. In this part, I also used the crown resin because it's a very stable resin. And then we let it go. And surprisingly, it went quite well. The distalization went good. And the biggest advantage is everything can be done in your own lab. Another case, we started with the distalization, and after a few months, the molars got distalized. Now we can begin with the braces. We can do it on the other side, like a Mesa slider. This was a 14-year-old female. And as you can see, she has missing laterals, and gratefully, the canines take position already on the right place. So we only need to mesialize the premolars and the molars. The lower jaw is not a big deal because we got mild crowding. And so I designed the mesial slider to mesialize the premolars and the molars. And then it went quite well. After half a year, the space is almost closed. And after a year, every space is closed. We still had to get rid of this crowding here a little bit. And then she got debonded a few months ago. And I think the occlusion looks quite nice. I'm not happy with this inclination, with this torque of the premolar, but I think when the canines have to be reformed like laterals, the patient should be happy. The next thing is my own copy of Wunderbar. Maybe you all know the Carrier distalizator, the motion to distalize or derotate the first molars, and also the power bar from American Orthodontics. So I think this is a very effective tool if you have to correct some dental class 2 occlusion, and if the compliance of the patient is good enough. It's a very simple appliance and also very effective. But what I didn't like is the length is limited. So if you want to use it, there are lengths from 17 to 32 millimeters, I think. And actually, you have to have every length in stock. So because you don't know how the distance in each patient will be. So I was looking to print themselves, and I named it. I copied the name of the power bar, like Wunderbar, and the great orthodontist Jörg, he gave me the name Wunderbar, and that is some kind of wordplay in German. So I designed a ball joint. I designed the ball joint, and this has to be this can be stick in, and it is as the original. It has some kind of derotational moments, but also some uprighting moments. So if you have some tipped first molar, or maybe the canine is still in eruption, then the vertical movement can also help in this case. This one I print with a flexible denture. This resin is usually used for denture base, and it has quite nice mechanical properties. So I think it was very suitable for my purpose. And as you can see, the material properties are very nice. It is quite flexible, but still stable, and it doesn't break so easy. But on the other hand, if you make to polish them or make them look good, I use OptiGlaze, and OptiGlaze is a very nice resin to make the surface shiny. But otherwise, resin is some kind of plastic again, and if you cure it, it can be break. So I have a lot of patients where the Wunderbar has broken because of the mastication, and then I had to adjust the design a little bit. Let's see a simple case. This was a perfect patient for this. Suppose he was skeletal in class 1, but dental it was class 2 because of the mesialization of the premolars and the molars, and we have a little bit lack of space for the canines. So in this case, I think the Wunderbar might work very nice. And the design in Onyx F is actually very simple. I only have to import the joint which I designed, and then I only need to make some bar and some pads on the buccal side. And for retention, I used a Graphie aligner on the lower jaw. But this was not a good idea. I will show you why. The patient compliance was quite nice. This is how we started. And a few months later, he was wearing his elastic very nice. As you can see, we have now space for the canines. And as you can see, I made a change in the design. I made the bypass of the premolars because to avoid some forces during mastication. And here we can see it better. And as you can see, we reached some kind of class 1 occlusion, and now we could begin with the braces, and then everything is working fine. But now what we can see is the rotation of the first molars in the lower, because the liners, they are not suitable enough to avoid the rotation. So for now, I'm using more lingual bars to avoid rotation, and then it is more stable. A few months later, now it aligned quite good, and we are heading to the end of the treatment. So the last part of my presentation is what is still possible, and what I will show now is some kind of experimental part. It was an idea of mine, and it is something which I don't do anymore because it is too complicated. But I started to do this, and this is just to show what you can do still with CAD/CAM technology. I was thinking about the buccal tipping of an RME, and as we know, the buccal tipping occurs on every transversal expansion with RME because we have forces on the tooth. And I had an explanation of Dr. Schwindling. He's the godfather of biomechanics in Germany. And he explained to me why buccal tipping can occur. Maybe when the hierarch screw is above the center of resistance, then we got more tipping moments. And when the torsional moment is not delivered enough, and if the bends are not stable, then you can also get tipping moments. Maybe the bend is not cemented very nicely, then you got also more tipping moments. And of course, when you do some arms, you got 1-point contact, and this might also lead to more tipping. And before he told me this, I started to think, okay, when you put the point of force appliance on the height of the center of resistance, and for this purpose, actually, I have to divide the RME, so I have the contact point here. So the appliance of force, I can adjust the height of the force system. And for this purpose, I designed a connector, and I tried to put them on the height of center of resistance, which is about 6 to 8 millimeters from the ground. And this was some kind of divided RME. And this part are the application of the force. And then I started with a simple case, and it worked quite nice actually. And I compared them, and the tipping was quite negligible. So I was quite happy that it works. I did some more patient. This was a quite easy case, but the expansion went very nice. And beside that, the expansion was very, very high. We got negligible tipping again. And also some elder patient, we did it with a power screw, and the tipping was in this case also negligible. So I think it was not a bad idea, but in reality it is too much work. So actually we need some more studies like CBCTs to look after the bone remodeling, or to look how the expansion in reality went. And of course, maybe the effort is not worth the effect, because Dr. Schwinding told me also, if we have a metal printed appliances, then it is so rigid that you transform the torsion of the screw directly to the tooth, which means you have almost no tipping. You will have tipping, but it is not so high as you use very standard bands. And this might be helpful when we use prefabricated bands, because they are not so stable. And of course, if I had to go on with that, the connectors needs more improvement. And Björn Ludwig helped me a lot to make a small publication in the JCO, which was also published last year. So I think we are quite good on time, and I would like to thank you for your kind attention. And if you have any questions, you can ask me anytime. Thank you.